one of the parameters that always been used in plant quantitative ecology is the density. Density is the number of counting units per unit area. So to define a density as the number of individuals per unit area is usually suitable for animals for which an individual is readily recognized entity. For plants, however, the above ground expression can be of individuals, or is it or it can be an intermixing of a few individuals with many above ground members, such as the gametes and also the gametes. Okay, gametes versus the gametes. Thus, a critical question the in the measure of density is to define the counting unit. A counting unit has to be consistently recognized by all observers for the density to be used as a monitoring method and quantifying the plant ecological system. So, uh, there are two ways or design or field considerations to determine density of plants in the field, which are the quadrats and measurement of distance. So first, we will go into the quadrats. We'll discuss about the quadrats. So three considerations are needed to determine density using quadrat, which are the quadrat design, the counting unit, and also the decision about the boundary. So the density of herbaceous plants is usually counted within the boundaries of a quadrat, or each of which is a sampling unit. We already discussed about quadrat design in the previous lecture, so I hope you guys can go back and review about a quadrat. Thus, a few pointers are reiterated here. Okay, first of all, you should have a practical quadrat size, and secondly, size and shape that you want to use must be suitable for your study, and thirdly, you should attempt to include at least some clumps of the target species in your initial trial quadrats sizes and shapes, or in another meaning, you need to have a good guesses on the size and shape of the quadrat. So determination of counting unit for density using quadrats is usually based on a count. You need to count, and usually they count the plants rooted within a quadrat. So plants with the root in the quadrat. So that's what means plants rooted. So it works best with plants with distinct and fairly small diameter stems, as the size of the area of the plant intersecting the ground increases, such as trees with larger diameter. So if the plant that in the quadrat have to bigger or become larger in terms of the diameter. So deciding whether a plant along the boundary is in or out of the quadrat becomes a little bit complicated. Therefore, for most species, the best counting unit is a rooted individual. But of course, for some species, other rules may have to be developed and also probably need to be right and documented. For some species, using rooted density or only rule is also problematic. For example, if the counting unit is a shoot of grass, you can find rice is the grass, and you can find a lot of shoots here. Okay, uh, if the counting is a shoot, if you counting in a shoot of grass, for individual tillers, okay, because grass usually have tillers here, so the different types of tillers and have different from the same individual you can find different types, a lot of shoots coming up from the same plants. So because of this different type of individuals are sometimes they are not clearly rooted. Okay, so for many method plants, okay, not only on rice, or for many method plants, trying to determine the root zone requires we need to lift and pulling out the plants at the from the top mat. So this can possibly causing injury to the plants. Okay, rice is not the mat plants. So sometimes the grasses. Okay, you need to crawl and then try to pick the plants. And sometimes you need to, because you want to find the root of it, you need to take it up, or you need to pull it out, causing the possible injury to the plants. Thus, for these method plants, using the canopy outline for boundary decision may be better than the rooted area. So we'll discuss about cover in the next lecture. So for this one, a more appropriate technique for method plants may be cover instead of using density. In addition, excuse me, in addition to identifying the counting unit, if you are interested to have more meaningful data, you should consider the value of using stage classes such as seedling, non-reproductive, reproductive, etc. Okay, doing counts. So you have a different stages. You have this reproductive or vegetative reproductive stage, seedling stage. Okay, uh, we, uh, you you can base your density, or you can base your count based on these different stage classes. Because doing counts by stage class, of course, doing counts by stage class requires more time, but in many situations the additional information warrants the extra effort. But you can get better representation about the density of the area, especially if you want to look or determine uh, the density changes of the same site for certain period of times, especially due to mortality or recruitment. So plants that can die, and also plants that can emerge from the from the seeds and everything. So you can find different types of the stages, and then you can find, oh, this is the representative of the density of the area. So especially you want to do the density over the time. So you want to have this year different compared to next year. So it's better to have to count based on the different stages of classes. Of course, the next consideration when dealing with quadrat is decision where to draw the boundary, which plants should be considered within the plot. Therefore, boundary decisions are important in density measures, since a plant must be counted in or out the quadrat. You must establish boundary rules and apply them consistently each time you do the survey, or you make a monitoring, or you want to do this counting. Of course, plant with a single thin stems are fairly easy to determine if they are in or out of quadrat, but plants with large basal diameter like trees may be half in and half out. Okay, how will this be addressed? Of course, which plants should be considered within the plot? Okay, first of all, try to avoid using the outline of the canopy as the boundary. Okay, try to avoid the outline of the canopy like this one, because changes in canopy will affect the density measures and increase the complexity of the interpretation. However, in such cases, most investigators use one of two rules. First, all the boundary plants are counted in on two contiguous sites and out on the other two sites, and or every other boundary secondly, every other boundary plant is counted. Okay, just to make it easy here, for instance here, plant C, D, E, F, G, and H, okay, will be considered by most observers to be plants within the boundary, and then therefore this will be counted. Okay, at the same time, plants A and B here would generally not be considered within the boundary plants, because only canopy, okay, only the canopy intersects the plots, although occasionally a specific situation may require that the canopy boundary be used rather than the Bessel boundary. Okay. Next, an alternative to estimate the density in quadrats is a technique called distant measures. Okay, we have this quadrat. So another one is the distant measures. Several variations on the theme have been developed, but they all involve the measure of the distance of an individual from a point or from another individual and estimating density from the average distance measure. Okay, this figure shows the four most commonly used distance measures in vegetation sampling. These measures are most often used for large or scattered individuals such as trees, for which the use of quadrats is not basically practical. Okay, it's not practical to use quadrat for the big trees, so they use these distance measures. They have, however, occasionally been used in grasslands on common herbaceous plants. Okay, this method uses distance along the transect line, so we can have this all the transect line here. Okay. Uh, and then depending on specific requirement, okay, these all have four specific requirement. Either the distance from sampling points, so every techniques have a sampling points. Okay, we want to get the distance of sample or the distance from the plants, okay, uh, to the sampling point or at the sampling point. Or okay, I'll explain one by one here. Okay, for instance, this one, the first one, the nearest neighbor. Okay, the distance, the measuring of distance between the plant. First of all, they identify this is a sampling point. First, they identify which one is the nearest to the sampling point. So they have this plant is nearest to sampling point. Okay, but the distance that measure is between this plant, the plant that near to the sampling point, to its nearest neighbor. So this one is then this distance is measured. So for this first sampling point, so this is the distance measure. So this is what we call as a nearest neighbor technique. So next is a point-centered quarter. Okay, now we have the sampling point, and then after that, once you create four quarters. Okay, you already have four quarters, and then you try to get the distance, okay, from the sampling points to the nearest plants or to the nearest individual for each quarter. So this is quarter 1, quarter 2, quarter 3, quarter 4. Then this is the nearest plants, and then get a measuring, and then you go up again, get another sampling point, and then you continue to do the same thing. Try to get all these four nearest plant, and then get the distance. So that's the second one. The third one, of course, are the nearest individuals. It's quite straightforward, where once you get the sampling point, then you measure the distance between the nearest the sampling point to the nearest plant. So this is what we call as the nearest individual technique. So this is very straightforward. So one, and the last one, a little bit complicated. A line is drawn. Okay, a line is drawn across the sampling point. So we have a transect line, but we have another line drawn at a certain degree. You need to define what the degree that you have, and then after that you identify the nearest plant to the sampling point. Let's say for here in this one, and then after that you identify another plant that are near to the second line here. So this is the nearest plants of the second line here. So we can have one. So this is plant number 2. So you get the distance between this plant to this plant. Okay, so this individual to this individual. So this distance is measured. So this is nearest plant outside 180 degrees exclusion zone. So you can go to the transect line and try, and then always do the same. Okay, so they try to find a random pairs from the sampling point to avoid bias. And of course, distant measures. are based on the concept of mean area per plant. So which means that once you get the distances, and then you get all the averages, and then you try to get for each plant, once you get the distance, and then you get what's the average distance from the sampling point to the plant, and finally you can calculate the density per unit area. Okay, most of the time, these techniques, however, are only suitable for use on plants with random distribution. Most plants do not grow randomly in space but occur in clumps, so the result of short distance dispersal of propagules or microvariation in habitat is needed to understand for this kind of technique. So most of the time, the nearest technique is basically you need to be suitable for uh, plants that are you look like is like a random plant.